thank you for coming to see our talk today about some of the work that Sebastian and I have done for the last 3 years of life. So Sebastian Scherer, illustrious professor here at the Robotics Institute, Field Robotics. But yeah,
Matt Travers, system scientist.
But yeah, so we'll just dive into it. So Sebastian and I we'll sort of stand all around here. This is meant to be informal. I mean, we'll present slides, and if anyone has questions along the way, please feel free to stop us. Yeah, so anyway, this was our approach to the DARPA Subterranean Challenge. All right, so for anyone who's not familiar with the challenge, this was basically, we'll describe it a little bit more and you'll see the details, but the idea was to go and rapidly gain situational awareness in underground environments. So there was several different sort of target environments that were supposed to correspond to the 3 years of the program. The first was tunnels. The second was urban infrastructure, underground infrastructure, so things like a subway system. And then the last was cave. So they weren't necessarily meant to be growing in complexity. So there was roughly 3 circuit events, 3 years, tunnel, urban, and then cave. Cave was actually canceled due to COVID, but then the final competition, which was just in September of this year, 2021, was actually a combination of all 3 of these. And we'll show you some videos from the actual competition. But yeah, at a high level, that was the challenge. So these are some of the different things. This is like the kitchen sink of, the full stack robotics is a phrase that gets thrown around a whole lot now. This was everything and then some. So all of the different challenges that we faced. So I mean, it was just everything from sensing to comms to planning to aerial robots to ground robots, multi-vehicle coordination, and then everything that it actually takes to make that work. So yeah, it was one of the reasons, right? So not everybody has this use case of being underground, but in terms of stressing your robots and putting them in an environment or a situation where, right, like you really have to go and solve the problems in order to make it work. So the actual objective of the competition was to go out and find and classify artifacts. So like things that you would commonly find underground. So like fire extinguisher, a cave, a helmet, simulated survivor, and to be able to do this as fast as possible. So this is a good way to sort of evaluate the capabilities of the robots while also making it like tractable to evaluate performance, because you can go and like measuring how good the map is starts to become a little bit complicated, but you can going out and determining how fast you can find 20 artifacts is measurable. Also to localize them, the artifacts, you have to correctly localize the artifact in a map that you're building and then recognize its type. So you have to have the perception, working with the mapping, and then have everything. For us, it was then sending that information back over the comms network to the base stations to go and try to score points. So this was the team year in, year out. There was a lot of people, so about 90 people, but lots of sponsors, and within the running jokes we have, like the easiest part of this competition was building the robot. But yeah, so they're just keeping all this straight and actually trying to get something to work. Was definitely a challenge, but it was fun. So it was a great experience with a great group of people. But yeah, this gives you some sort of sense of the scale from the different competitions. Our win theme, if you want to think about it that way, or like the thing we really hung our hat on from the proposal stage, and then really tried to take as a main sort of philosophy throughout the project, was this idea of modular autonomy. Modular robots, anyone who's ever seen Howie give a talk or seen Julian give a talk has heard us talk about this theme in general, and starting to really reimagine what we mean by like a module and a modular robot, right? So it's not just like a classical mechanical component, like I have a drive module, but really starting to think about the mechanical component as well as the software infrastructure that underlies it necessary to actually use it, right? So I don't just have like a motor module, I have motor modules that can be connected to other motor modules, and really starting to think about the interconnections of things, and the mechanical side, getting into the software side, and really having this this idea, one of Sebastian's ideas, is this like redundant, or yeah, resiliency through redundancy, which means sort of at a very high level, like I don't want one planner running because that one planner could fail, or one planner could fail. I want to have multiple planners running simultaneously and then have something else arbitrary between the planners. So if something breaks, I'm not dead in the water. And that idea, and really trying to push that from the hardware level down into the software level, so that it's just a sort of systems philosophy, is one of the things that we really tried to do. All right, so for better or worse, all but the Spot robot, we built all of our own hardware. So it turned out to be 3 ground vehicles, a bunch of drones, so 7 drones in total. These custom drones that we built, this was a company that was actually started by 2 former Robograds called Canary. These larger drones, and then everything else was custom except for the Spot, but the payloads on everything were custom. So there are several different generations of payloads, and a ton of hardware that we built. So one of the interesting things, and I guess I'll show this in the next slide, that for us was a huge challenge was, you go out and design autonomous robots. I can tell you how to do inverse kinematics, right? But like having to deal with the communications underground, so it's primarily line of sight. So you can't just stick a radio down a tunnel and hope for the best. Like it is actually mostly line of sight, depending on what your radio is. So this is a huge problem. I mean, this is not. We still haven't solved it. I mean, we've barely even scratched the surface after 3 years, to be honest with you. It was like one of the things in the final competition that gave us a lot of pause was actually the comms, and we'll get more into that. But these were something we were particularly proud of. The robots, they actually did, so it autonomously laid out these nodes, and I'll get into some of the details on this as it went down. The tunnel, so we built everything other than the radios, everything to drop the nodes, the whole 9 yards. And then this gives you some, sort of high-level systems diagram for the actual autonomy itself. So again, it's like everything in the kitchen sink, but it's a full stack, right? I mean, it's starting from scratch, and then you have to do everything, right? From the low-level controls, so sending motor, controls to the motors, all the way up to the mapping, the estimation, map building, and everything in between. Modular, resilient, and scalable, I guess, is our sort of overall philosophy from the autonomy perspective. All right, Sebastian.
Okay. So I think like Matt said, so there's a lot of cool technical things I think that we implemented and developed over the couple of years, and we just want to show you a couple of them. Unfortunately, we can't show you everything. That would take probably half a day. So we just kind of picked a couple of things to highlight. So I think one of the things that might also be kind of interesting to some of you is we developed a SLAM algorithm, and there's a lot of the people from the team also in the audience here, so if there's any detailed questions, we can also defer them here. And so the idea was, the high-level idea for this was that IMUs can give you very good data for SLAM, but they usually used as kind of an afterthought, or just to kind of as an initial guess. And the idea was to try and turn it around and use the IMU as kind of my main source of odometry, and then use external sources of odometry as a way to correct the drift of the IMU. And so it's basically a couple different smaller factor graphs that are set up and interact with each other. And so that was running on all the robots, so all the mapping results you see from here. And another thing we had to look at is, how do we make this work in a wide range of environments? So one of the things we wanted to avoid is, we can't just make it work in hallways or a cave or a tunnel, right? It has to work in all of these environments. And so some of the things you can get away with in a kind of research algorithm, we actually had to address. Like, for example, here, it's automatically trying to scale which features are used for calculation depending on the size of the environment. So if you're in a hallway, use more features from closer in. If you're in a wider open space, use less. Similarly for computation, for example, the drones can process less than the ground robots, so they use a different computational budget, and so it's adjusting to that. Or here is another example of dust. Typically dust will cause a lot of features close by that your SLAM algorithm might get confused by, and so detecting that dust and then ignoring dust is kind of another feature that's kind of in the that we essentially had to end up developing. And so we also, kind of, as part of the challenge, we developed, for example, also, we developed the different pieces, right, like visual, LiDAR, IMU, odometry. In the actual challenge, we only used the LiDAR component because that was the most mature, and some of the visual parts didn't use enough, used too much computation, and we didn't feel we're mature enough, and actually we didn't need, because it actually worked good enough. But as part of it, for example, here's a visual part. So if you're in really degraded situations, a LiDAR alone will not give you enough information. And then similarly, part of the challenge was to push. There was fog in the environment, and so if the fog is really dense, then you can't see through it. So we also developed thermal inertial odometry that can keep estimating in fog. But it actually turns out in the challenge the fog wasn't dense enough to really be an issue for a large issue for the odometry. So we did not deploy this. Now. Part of the challenge is object detection and to localize these objects, like Matt mentioned. And so, it's actually, there's a lot more than an object detector that goes with it. And I'm sure you can't see that chart, but it's really to just tell you, hey, there's a lot going on. And so, just to give you an idea, is we have to find gas as well as Wi-Fi as well as visual objects. So, well, you don't have to find Wi-Fi, you have to find cell phones, but finding cell phones visually is very hard. So finding it via Wi-Fi or Bluetooth is much easier. And so then, a lot of the other boxes here that are green and orange really are about how do you combine all these sorts of measurements into a consistent estimate that then gets output at the end. Right. Also, we worked on trying to, it's a fine balance to balance between false positives and what was the other one? Anyway, so basically you don't want to, you don't want to miss any objects, but you also don't want too many false positives, and so that's like a very tricky trade-off. Well, we'll find out how that worked. Turned out in the final competition, but so you can see how that works. So you see some object in the camera, and then or in the thermal camera, you have these detections. Those detections get raycast into the map to get a location, and then for gas, we essentially create this kind of signal cloud and try to find the peak of that measurement, and that's kind of the one we say, hey, this is where we think the object is, and then there's a manual adjustment phase where we try to put it to a door is what we have to report to for the gas. For the visual objects, we basically create a bunch of 3D estimates and then cluster them together, and then we create an object detection that gets sent to the base station. And so those estimates can come from visual as well as the thermal camera. There would have been also good opportunities to do 3D object classification, but we, for time reasons, we didn't get there. Let's see. So On the planning side, so I think we'll talk about a couple of different kind of interesting bits for the different robots. So one of the things that's for the drone side that's pretty hard is how do you fly through narrow spaces? So our drones are 60 centimeters wide, and we want to fly through spaces that are maybe 10 centimeters wide and like 70 centimeters. So the drones essentially detect when there's a narrow passage, line up, go through, and then fly through these narrow spaces. So you can see here, this is from the final competition where the drone flies. Also, we want to fly as fast as possible since our flight time is limited. We only have 10 minutes, so we want to really go fast if you get the chance. So here's a wider open space, so the drone will try and go about 2.5 meters a second and cover as much area as it can. So once we can fly, we have to figure out where we're going to go. And so the other thing to keep in mind is that all of this has to happen in real time on the robots while all the other pieces are running, where they're running SLAM, object detection, flight control. So there's a lot of stuff happening on the robots, so we have to make lots of trade-offs for all the different components in terms of computation for SLAM versus how much do we give to planning versus exploration, object detection, and so on. So for the exploration, a large part of it is, how do we get it fast enough and within enough computational budget? And so the approach we took is the following. So the other thing that's worth noting is that it's not purely an exploration problem, right? Like your typical classical exploration, you'd say, okay, how much of the map have I seen, right? So it tells you, like, if you have your LiDAR, if you move, how much of this wide area have I covered? But that's actually not what we care about. Is we care about how much of the green have we seen. So the green is here, all the images that we have taken and where we have looked to see if there's an object, right? And our range to detect objects is much less than our range to build a map. So the range to detect objects for the drones is, for example, I think around 10 meters maybe. And the range of our LiDAR is about 100 meters. So we can build that map much further out than we can actually cover this area. And so it's a trade-off between coverage and creating coverage of the wide map versus discovering more of the map. And so here are just a couple of examples of various deployments. So this is from the urban circuit. The previous one you saw was Laurel Caverns. This is from the final circuit, showing of how this exploration looks like. So here the drones also this is from the final circuit in like the tunnel area. So you can see it's this orange path here is the planet's building, and then it's exploring in 3D, trying to look for objects and essentially cover as much of the map as it has found. And here you can kind of see going into some of the narrower areas. So part of the challenge for the exploration is often to, so in these larger areas, for example, how do you trade off between covering a wide area very well versus going to a smaller opening that could get you to even more information to find, right? So that's often a tricky challenge that we have to navigate. See if there's anything else. So here's, for example, some of the experiments at Laurel Caverns. And so the robot will explore in 3D, so it will essentially go up and down, and it's not really afraid of getting close to things. One other thing that is a bit of a challenge with the particular setup of a robot is that we have a Velodyne sensor on there, and it only has a 30-degree field of view. So when you're flying in something that is very 3D, it's difficult to decide, can you actually go up or down, or is there more to explore? And so, for example, Laurel Caverns has a 30-degree kind of slope, which is exactly at kind of limit of what you'd actually see. Here you can kind of see a fast forward of an entire run inside a boiler, the steam boiler plant. And so one of the things we'll talk about a little bit more later, but what makes this really tricky is you want this to be resilient, right? Like sometimes your robot will get stuck, sometimes there's dust, and we'll have to recover from all of this. Let's see. Fast forward a little bit. Here's inside a coal mine. This is tour at mine. This is going down some stairs. So you can, so the robots will also coordinate with each other by kind of two ways. So they share the covered maps with each other and what are promising areas to go to. And then the other part of it is they also share roadmaps. So if some robot finds a promising spot, the other robot knows how to get to that location via the roadmap. And here you can see some of the maps, of what we then end up. Okay, and so I think I'll hand it back to Matt.
All right, cool. Thanks, Sebastian. All right, so for what it's worth, so we did have Sebastian was talking about the aerial robot coordination. So we did use two different coordination strategies for the ground and the aerial robots. The best of my understanding is because with the aerial robots we had to do viewpoint planning. With the ground robots we had cameras pointing in all four directions. So with that, the actual viewpoint planning problem was a lot different. So yeah, this is a paper in fact Chow wrote. I think won like a best systems paper at RSS this year, which was basically the global planner that we did used in the competition. And it worked. It worked well. So, the illustrates what you're looking at here is a map from the final competition. So if you've seen outside of my office, this is where R3 actually went off the cliff. But the coordination, in terms of how well the ground robot, and I guess the total coordination really worked. So we did explore the most area. We saw like 95% of the map is our little feather in our cap, so to speak. So yeah, it was a hierarchical thing, right, where you're basically planning in the global map, and then within each sub-region, you then have a local planner. But yeah, I would highly encourage you to go and talk to Chow or read the paper. But it was impressive. I mean, by the time we were getting ready for the final competition, it was like set it and forget it. We were testing at this like abandoned hospital, VA hospital, down the road. It was an illustrious 3 years. And it was, I mean, you literally hit the button and the ground robots would go out, and an hour later, the run times were an hour. Typically they go out of comms, so it's a big complex. It's like 12 different buildings that are all connected.
So the robots would just go out, and an hour later, basically, they'd come back. Yeah, it was impressive. Short video of the ground robots. So this, the prize round, what you're looking at, this was a set, like, that they, DARPA created. So everything that you're looking at was built on the inside of a mine. So they had like a Hollywood film crew like come and actually like design this set. We drove through one of the walls one day. But all of this is created just for this competition. I think there was an article from Victor from DARPA. I think the whole program was 87 million total. So I think they spent 10 mil just on building this. So it was the real deal. But all of this was created by them. They made it really look like there's a mine out in Colorado that we were at for the very beginning of the competition. There was this Sticks event. This is almost exactly what that mine really ended up looking like. So they did an amazing job. But this is just showing you the mobility. We had the 3 ground robots. 2 of the ground robots actually got stuck, I think, in the final competition. But this, the R3, the robot that eventually took the dive off the cliff, it was amazing. Like, watching these videos of it gutting through all of these spaces and just plowing through was yeah, cool. This is actually showing you just some of the different stuff. But yeah, a good little robot. But yeah, it was amazing. So we're happy to share. That's one of the dynamic obstacles. So DARPA during the final competition, they changed the map by having dynamic obstacles, so you couldn't just like, leave a trail of breadcrumbs, so to speak, and then come back. This was the final ascent. Worth watching. It was the only robot I think that, I didn't show it. It was the only robot. Oh, yeah, we'll show it later at the end. But it was the only robot that made it actually up. I think it was the only robot that actually made it back there and up onto that ledge. Although I guess no robots made it back there. But yeah. Cool. So another thing that was cool was, right, so the robots, ideally, right, you'd send your robots out and they'd go in different directions, and you wouldn't have to solve the coordination problem necessarily, or not that you wouldn't have to solve the coordination problem, but the coordination problem would be much simpler to solve. Right, you go that way and I'll go this way. But I mean, you can sort of see from the map, the final competition, the actual area turned out to not be that large. So one of the things that we had to really be prepared for was if the robots meet each other, what's going to happen. So especially like in a narrow hallway, like how do you deconflict? And yeah, definitely the details that you need to think about. So this is cool. We had this. It's basically like a dynamic, dynamic do not enter region, which is based on both the robot's position and its speed. So it has this like imminent collision region where it'll actually, again, sort of project forward using just the simple dynamics to see, basically it's forward velocity to see if, in the future path, the 2 robots are going to collide. I guess there's a view of this. This is roughly what it looks like. Whereas the robot starts moving, you'll actually see the obstacle start to grow. And yeah, we didn't, it's actually way more difficult than you would think to make this work in reality. But yeah, we actually didn't have any robot deconfliction errors or anything. So yeah, it was cool. All right, so this is another, sort of what's in the sausage, so to speak, and of tools that will persist well past Subterranean Challenge in terms of just like raw engineering. There's a lot, right? So just say that you're going to have a multi-robot, multi-agent system is cool, whatever, you can go write papers about that. But if you're going to go try to make this work like in reality, and you're going to have this, the the coordination, the mapping, and the exploration, you need a lot of foundation. You need a lot of plumbing to actually make all of that work, right? Like having two robots be in the same area and having them have a mutual understanding, right? Like this robot has its map and this robot has its map, but knowing that things in those two maps correlate with each other is easier said than done. So part of the solution that we came up with is basically this ledger system, where the robots are always basically sharing, so they're doing a handshaking and always just sharing information with each other so that everything is consistent. So the robots don't have to have, so if the robots are out of communications, right, they don't have any communication, they don't have any information from the other robot, but if they come into comms, even if they're not connected to the base station, like they just meet each other outside of comms, you know, a kilometer down a tunnel, they'll actually do this handshaking procedure just over the wireless communications where they'll share information and make sure things are consistent between them. So this is cool and it's easy to illustrate from maps. One of the really cool things that we got out of this, or got out of this downstream, was that it made it possible for the robots to also share artifacts with each other. So if one of the robots went out of comms and saw a bunch of artifacts, we could send, and we did send, a drone. Actually, one of the ground robots got stuck during the final competition. We sent a drone out to basically go fly by the ground vehicle and then come back to the base station because it got all the artifacts off of the ground vehicle that was stuck. And all of that just happens automatically. Automatically via the ledger. So it's, we're sharing not just maps, but all of the sort of pertinent information between the robots. And like to really go and make this work. A lot of the other teams, it seemed like, had something similar, but this worked very well. John, who's sitting somewhere out there, was instrumental in helping to put this together. So this was 3 years ago. I knew very little about communications underground for autonomy. And we started out with wireless repeaters, basically nodes that you buy, whatever, Best Buy. And they were one of these canisters that got dropped out of the robot. This was cool. The mechanical design was all done here. It was basically a latch that sat in a solenoid. So it's basically when it's active, it's in the latch. You apply current. Latch opens, solenoid, and then it's gravity fed, so the nodes actually come out. So there's multiple generations of this thing, of the node dropper. Oh my god! Going back, so that was like the most complicated mechatronics project ever. Was this node dropper? But it was beautiful. I mean, by the time it ended up working, really, really well. I mean, it was. It seemed robotic, for lack of a better description, if you actually watched out how it, which is good, right? Like you want your robot demos to effectively be boring, and this is working well. I guess I'm quoted. But anyway, so we had to figure all of this out from the ground on up. So there's the mechanical aspect of it. This is cool. So I had actually two master's students who did they wrote their theses basically just on doing the, so there's multiple different levels at which you get to sort of think about optimizing the comms. So through each one of the nodes, you're going to get losses, right? So like it's not just like you want to drop as many nodes as you possibly can. I don't know if you saw in the last slide, we only had 24 of them. So you're going to sort of be smart about where you drop them. And again, it's very geometry dependent. For the types of radios that we were using, I mean, it's effectively almost just line of sight, especially, and it depends on the environment, I should say. But thinking, you gotta be smart, long story short, you gotta be smart about where you drop the nodes, because you only have so many. So we took into account sort of like signal strength, the actual distance, and then line of sight, so the geometry of the environment. So you're actually using the map. So the robot, for example, if the robot's coming up to like an intersection and it's already at like the distance where it thinks it should drop the node, it'll wait to drop the node for the intersection because it's a better place to drop the node. And this is just some of the optimization. So RSSI is just the signal strength, for lack of a better description. And then this is still like I mean, well, we were doing some basic flow control. When you start to have, like we had 10 robots all just on one wireless communication, like ad hoc wireless mesh. So this is sort of getting down a little bit lower, which is, like you can't, even during nominal performance, you have to have something which is regulating the flow, or it'll just go crazy. So you need to, this is like, you can optimize at the application level, which is like, I'm not gonna send more information than I have to, but at a certain point, like you just have information that you have to send. So figuring out how to go and do basic flow control and everything, the entire thing was optimized. I know it was years worth of work, but it was cool. It worked. It worked perhaps too well in the final competition. So yeah, this is just again sort of what's in the sausage, but telling you how we sort of did the prioritizing. And yeah, I worked a ton. So Ryan Darnley, somewhere around, but yeah, I did a ton with working with DDS. And really just optimizing the whole entire comms pipeline was just 3 years worth of work, easily. All right, cool. I'm going to back over to Bash here.
Okay. So we talked about resilience, and so here's some examples of what that looks like for the UAVs. And so. For example, fog and dust can be real problems. Also, we don't have access to the robots, right? So the robots always have to find a safe place to land. So here's an example of what happened in the final competition. DARPA put out some fog in this tunnel. Eventually, that fog gets so thick that the robot can't decide if it's flying into an obstacle or not, and then decides to rewind, and then it actually, the slam drifts a bit, it gets stuck on that sign, recovers from that. Then actually the other thing that happens here is this red line tells it, hey, this is a bad area to fly, so this is actually blocked off for exploration, so now it's trying to go to explore in some other area. Here you can see the emergency landing site that's evaluated. So this green circle here is an area below the robot that's always checked if it's safe to land. And it always keeps track of the last safe location. So this is in Laurel Caverns, which is very sloped, so there's not that many good places to land. And so here, it's flying over some ledge. Then here's a good place to land, and then now it's essentially flying up the staircase, and you can see there aren't really any good places to land. And that whole process takes it too long. It's trying to return home. That whole return home time is too long, and so it says eventually, I can't make it back home. I got to go to the emergency landing point, and so it basically comes back and lands. And so all of these kind of behaviors, there's more of them also for exploration. If it's one of the exploration fails, it will switch to a different exploration. So the robot always has to do something, and there's no operator to help it, right? And so so there's a lot of little interesting cases in there that come into play. Similarly, for the UGVs, sometimes they might get stuck, like here in a door, or other areas where maybe there's fog, they can't decide what to do, and the ground rovers always have to keep on doing something. So they also have two things. One is a tip-over recovery, so there's a certain angle where they will basically then undo what they just did to try and avoid tipping over. And then there's also stuck recovery behaviors, which you can see here, where the rover gets stuck, it will start and execute certain back and forth motions to try and get itself out of a situation. And those motions happen blindly. And there's actually good motivation for this. If you're in a tunnel, as long as your angle, for example, with respect to the wall is shallow enough, even if you just go straight, right, you'll basically bounce off the tunnel. In the final competition, the walls weren't as solid as what we were used to, so we drove through one of the walls in a situation where we got stuck when we tried to get ourselves out of a difficult situation. And our base station, the idea is kind of two things. We want to be able to know that the robots are working, right? There's some status information. And the other one is that before we send off a report to DARPA, we basically review it to make sure that we like what it looks like. There's some picture with it. We make sure that the object detection did a good job in terms of classifying or change the classifications. And so our operator, which is Chow, he also in the picture, basically goes through this list of artifacts and then decides what those artifacts are. Something else that kind of I think turned out pretty interesting is so we used behavior trees to encode the different behaviors and states that a robot could be in. And I think as an operator, even though there's a tiny picture, at some point, you can basically just look at this and get a kind of intuitive view of what's going on, right? Like after you've seen the robot do enough things, you kind of have this, as a human, you develop this kind of pattern match very quickly. Let's see. Additionally, you also have a map basically associated with the artifacts. You can check where the location is of these artifacts. So I guess now we come to how do we do? And so just to kind of summarize, so for the tunnel circuit, we placed first, more than 2 points compared to the next team. For the urban circuit, we placed second, and then for the final circuit, we placed fourth, and like Matt said, we explored most of the course. So I want to give you kind of a couple minutes rundown of how that competition happened. And so maybe before I start, so up here you'll see the period that time period in terms of 0 to 10 minutes and so on of when that what was happening. And so on a high level, we send out R2 first towards the tunnel circuit, send R1 towards the urban circuit, so that's in blue, and R3, the small robot, to the cave section. R1 now turn around and is launching a drone. You'll see a new icon pop up, a yellow one. R2 is stuck in the tunnel in a big area of fog. Here the drone this is the section that I showed before where it gets stuck in the fog. R3 is out to explore some cave environment. And R1 is off exploring more of the urban circuit. And so at this point, R1 is exploring more of the urban area, and then R3 is still off, R2 is still stuck. Now, let's see. So I think by at some point here, R1 is going to go through this an area that is a little tunnel section here. You can already start seeing. It goes down this section that the drone explored before, and through this area. Here's this section coming up where the dynamic obstacle closed, and I think somewhere around here, this area kind of slopes down. We lose communication with R3 somewhere around here. And at this point, we're about halfway in. We've explored most sectors. R1 is stuck in this cave section that kind of was like a funnel environment, so it's stuck here. And so the drone that we sent from the base station essentially gathered the objects that R1 didn't communicate back. So R1 lost communication with R1 somewhere in this tunnel section, and so the drone basically flew in and was able to gather it. Now by this point we know that we haven't heard from R3 in a long time, and we're trying to figure out what's going on. And we know R1's stuck. So R2 is coming back finally out of the fog. It kind of got itself free. So I think we sent out we sent out DS1, another drone, to try and potentially gather data from R3, but we actually didn't know that R3 had fallen off a cliff at that point. I think we had no communication. We haven't had communication with the robot for a long time. Also, I guess R1 was actually wedged in the cave here, so it wouldn't have been able to get through the cave, but potentially might have had actually communication. So the last, I'd say, 20 minutes we're mainly focused on looking at artifacts, and so I think received around 500-600 artifacts reports, which was much more than we had ever seen before, and so it took our operator a long time to go through these artifacts, and so that was kind of the run in a nutshell. And so you can see here, this is the combined map of the 3 ground robots. And so this is purely, so the way we create this registered map for the run is the first robot, so DARPA establishes a coordinate frame. We calibrate the first robot, which I think might be R1 or R2 to that. And then all the other robots localize to that first robot that we calibrated, and that is mainly to save time, because the calibration, we basically take 2 points with a total station, a survey instrument, to establish that reference system, but then doing this alignment is much quicker. And then these are the maps for the free drones. One of the things that's kind of interesting to observe is that since that typically our ground robots would cover much larger areas, so they would drive on the order of kilometers, but since that map was so small, actually the drones and ground robots cover similar distances. Now here's kind of the could have, should have, might have slides. So we kind of ran, because we had such a big list, we ran out of time to really go through everything. But if you had just submitted all, so there's a period where at the end where we typically submit all gas and cell phones, because they typically require some refinement, because we only see this cloud and it tries to find a maximum location, which isn't very accurate, and then we just kind of look in the map a little bit and take some educated guesses. But if you hadn't done that and just submitted what we had in the base station, we would have placed third. If we had time to essentially adjust cell phones and gas that we had data for, we could have potentially in first place. And if you had gotten artifacts from R3 before it fell down a cliff, or actually, if our strategy hadn't been as aggressive, and we had just submitted all the artifacts, our score would have been 24. And if you had everything together, it could have been 29. So, yeah. Anyway, so I think, this, just to kind of summarize, I think there's, in these challenges, there's often, there's many factors, many knobs, and many strategic decisions. We went with a very aggressive approach, right? We deployed, very deep into the course with a lot of depth, and that's also why we explored most of the course. and but it was a higher risk strategy, right? Anytime you go deeper before coming back, there's a chance that you might not get your data back, which is kind of what happened to us. I think I think there's beyond what the score we got. I think we were able to deploy a lot of very high-risk technology successfully. I think that's something I'm very happy about. In terms of, like, for example, this kind of coordinated exploration or mapping. All these things are. There's of course a lower risk, maybe more reliable way to do this, but I'm really happy that we were able to do the aggressive part and actually worked. Just a couple of lessons maybe for future work, but there's a lot of lessons learned which I kind of left out, which we can talk about maybe in the Q&A. But so I think one of the things that was kind of high-level thing is drones were a bit too big. Exploration had this kind of trade-off between larger area and doors, which is a little tricky. The object detection for the challenge is very artificially constrained, right? In a real-life application, you'd really have to learn this object detection very quickly. And I think the ground robots also, you're very good for tunnels, but maybe a little big for realistic situations, and just in terms of transport. There's some things in terms of, for example, the user interaction on the base station, which we could have done. Like, for example, having higher priority, having more confident detections, sorting by confident detections, and having some more relevant capabilities. And just to kind of end on a lighter note, here are some bloopers. So this is the video that Matt wanted you to see before. It was a little unfortunate, a little choppy of our robot falling off the cliff.
Definitely a robot flipping over right here.
I'll just pause maybe somehow, something will go faster. So it's trying to actually come back up now. It realized that it can't make it, and then it just drops off and then lands at the bottom of the cliff. So, and then on the top right here is a slow motion video of a drone disintegrating in flight because of some oscillation. So that was also an exciting night, which is the picture to the right here. Trying to get that ready for the test the next day. Let's see. So I think, so this is the last slide here, and of course, I didn't mention any names. I guess there's a lot of people. I'm just kind of the reporter here, right? Like, there's a lot of work, a lot of awesome people that I'm glad that we could share with you. Thank you.
Questions from the crowd?
So I have a question about the use of LiDAR on the drones. So why was purely visual, localization or just purely visual information not enough in the caves? Or I guess another way to put that is, how necessary was LiDAR information?
Yeah, it was much more reliable, quickly, right? I think it's kind of the end answer. Doing visual SLAM in dark environments is very tricky with little drift, right? Like, you wanted to have less than 5 meters after 200 meters through very ill lit situations. It was just not possible 3 years ago, right? Or maybe it's still not possible today, right? So yeah.
How did you balance production and testing, working on the robot itself and testing in different cities?
Yeah. I mean, that is a tricky That's a very tricky balance, yes. And I don't know if you balance it the right way.
Not well.
Because, I mean, it is, ideally what you would like to have for this type of project is a test team and an engineering team, and the test team is not allowed to talk to the engineering team, right? I mean, I think one of the things that's very dangerous if somebody who develops tests is that they'll change the environment to make the robot work, right? and that's not something that DARPA would do, right? So that was something we had to really hard, fight a lot to make sure that that doesn't happen to us.
It works, means something different. Right, so like if someone's actually developing the application, their part might work the way they wanted it to work, but when you go with the full system, breaks everything else, but it still works to them. So having that firewall in between development and testing is pretty good. Yeah, right.
Question about, do you have a sense of how different were the solutions developed by the different teams, or did everybody sort of converge on a similar system?
So there were a couple of different differences. So in terms of, everybody was doing kind of LiDAR SLAM, let's say. The approaches were a little different for the different SLAM systems. In terms of actual, for example, exploration, it was pretty different. Some of the teams were mostly like waypoint, teleop. Some teams did like single robot exploration, like for example, I think, for example, Cerberus didn't do any multi-robot exploration. They just basically did single robot with some biasing. And I think the object detection was pretty similar. The general approach. I think user interfaces were quite different. And maybe that's something that we should have invested a little more effort in. At the end is making sure that some things like sorting by likelihood that this is actually an artifact or something like this is something that might have been a useful feature that we after the fact are a little smarter about. But,
Yeah.
So was there any restriction on the number of robots you can use?
no.
So for a backup, like if we have a small drone on top of every robot that can carry the artifacts back, like if it gets stuck, is that possible like with such a design?
So we had, maybe that didn't come out, is actually, you can kind of see it here. So there was a drone on the back of, so we actually had the option to have a drone on two robots. In the competition, we only launched a drone from one of the robots. And so that would also then actually register to the rest of the map once it takes off. And so, we didn't launch two drones because the map was so small, it wasn't necessary.
The drones for backup, like if the ground vehicle gets stuck, then the drones can just carry the artifacts back.
Well, they also themselves find objects. They don't just carry artifacts. Yeah, they do the full mission. But the artifact kind of carrying is every robot can carry anybody else's artifact. So think about it like BitTorrent essentially, right? BitTorrent for robots. So they'll, right? I mean, one robot has one part of the object detection movie, and the other part of the object detection movie, and they together they'll have the whole thing. Yes.
Yeah, I have another question. How autonomous was the recovery behaviors of both the drones and the vehicle?
Right, the recovery was all autonomous. So basically, because often, mostly, we wouldn't have comms when they return. So the ground robots would have a time that it would come back at, say, 15 minutes into the run to give us 10 minutes to look at artifacts, and calculate, hey, how long does it take me to get back from where I am right now? And even beyond that, like you saw the thing closing, right? Then they would go out and actually try to find an alternate route home. On the drones, it was a little different. So the drones would also calculate how long it would take them to get back. But if it's blocked, they don't have as much flight time, so they don't have as much time to like explore and look for other places. So they will just look on the map they've built so far and try and find some alternate route. So they wouldn't explore more to go home. Yes.
What was your favorite moment from the last like 3 years? Like, what was your favorite moment during the whole competition?
Can you say giving this talk?
Yes, probably. Yeah. Finding some closure. Yes. No, I mean, I think there were a lot of. I mean, it's, it's. I think always, field testing is very painful, but it's also a lot of fun, right? I think there's some really unique experiences, and just kind of. I think it's a lot of moments I'll remember. I mean, there's like there's a lot of. A lot of moments.
For me, the final competition, I mean, when everyone was just, things were finally starting to come together. I mean, we got 4th place, but, it wasn't like it was embarrassing before. I mean, it worked well. It's just we beat ourselves. But yeah, just those final days, just grinding. I mean, there's a little sleep, it's high stress, but just, seeing everything actually come together and having everyone in one place and just like, really working it out, working out the problems. Cool.
And I think it was really awesome. It was a really awesome team, I think, to work with. Like, everybody pitched in and did kind of 100% to make it work. And, it's really, it's kind of fun if everybody pulls on the same string, basically, and everything comes together. We had like, we had changes. Yeah, there was a lot of things till the end. But definitely.
During the animation, you talked a lot about like how a robot noticed that it was like disabled, and then how others acted on that. So like, how would you determine that, and then how would you determine what other robots would do after that happened?
So there is still. So there's the high-level thing, for example, the rescue part and so on. That's like initiated by the really high-level coordination is initiated by the operator. So you'd say, okay, let's send the drone out. I know that this robot is probably stuck back there. Let's send a drone there, and then once it's there, it will fly by, and then we'll start exploring, and then come back home, basically. When the robots are stuck, or so there's this detection basically where they detect, hey, I'm stuck, or I don't know where I'm going. There are different types of stuck detections, and that will trigger these behaviors. Basically, they measure how much progress they're making to what they're expecting to be making.
Yeah, good question. So obviously, this was a 3-year development process timeline. We're getting like a kind of a post-review. But during the actual process, was there a technology or capability that was deemed too risky at the time of development, and which was actually developed it earlier, or
There's a lot of these. Like I mean, I think one that we're kind of coming back to was, like Matteo asked about vision for drones, right? Like there was a time we actually built a whole payload, vision payload with 6 cameras and so on, trying to do a vision drone, right? And it was too risky, right? Like it was too big of a jump. I mean, I think there are other examples. Like maybe some autonomous stair detection or 3D object detection, or let's see, yeah. Yes.
All right, cool. I'll just do one last question. Going over a little bit. How about you, Dan?
Did you ever decide to prioritize any objects to detect over others? Like you said that you had to do some processing with the operator for certain like gas and stuff.
Right.
Whereas maybe other ones would need less validation.
Yes. Right. So the gas and cell phones we basically always keep to the end, because they would require the operator to kind of fiddle around and maybe guess a couple of times, and so those we will keep to the end. Yeah. But there was we did kind of, there's a tendency for these objects to kind of accumulate up and then submit all of them at the end, but then you kind of run out of time. So we said, okay, we'll have periodically our operator would review what is in the queue and then submit it.
So before everyone goes away, I have 2 comments. Is there a PSR today?
Yes.
So apparently everyone knows about it but me. That's good. The other thing is, for the follow-on project, as the 2 of you are in a follow-on project, are you recruiting for talent for the next one?
Always.
All right, so you all heard his recruitment pitch.
Succinct. But yeah, there is, we have 2 different projects that are both ongoing right now or spinning up on one of them. So we're doing a convoy problem, so smaller scale than this, but fast driving convoy with vehicles with some of the same payloads. So multi-agent coordination there, lots of control stuff, lots of SLAM, lots of stuff to figure out. But we're basically porting a lot of this work, and a lot of the stack from SubT is going directly into that. And then the new DARPA project, Racer, which is full-size, autonomous, off-road, high-speed racing. And so, again, starting with a lot of the same components here, but really trying to push them as far as we can go at high speed and fully autonomous. Oh yeah, and sorry, then there's another DARPA project, which is also starting, which Howie's going to be the PI on, which is stair climbing, which is basically like the logistics support in urban infrastructure. So being able to lift heavy payloads upstairs, downstairs, cross gaps. So a lot of mechanical design on that one. That's going to be spinning up as well. And we're using a lot of the same tools that we did here, so autonomy, mapping, the semantic architecture. But yeah, so those 3 projects, if anyone's interested, please just shoot me or Sebastian an email.
And the other thing to note is, what I'm hoping that we're going to do is, like when these guys started the Explorer, the hope is that we're going to start to create an infrastructure in the departments for these kinds of capabilities that we can plug and play eventually. It's a nice dream, but I think it's one that we as a group this group here can do. So I'm really hoping to sort of suck effort out of all.
That was his pitch.
And then yeah, so we are taking some of the stuff also for the drones and essentially now building a vision-based drone. But anyway, so there's a bunch of papers that came out of the project, and there's also more papers that will come out, I think, probably, sometime next year that are related to this.
And there's a best paper that came out of this.
Yes, there are more than 1. Yeah.
Oh, 2. My apologies.
Chow had one. All right, cool. Thank you. Thank you, speaker.